Hello, I'm Robert Miner, and this is my How It's Made video on Gorilla Glass. So what is Gorilla Glass? Gorilla Glass is a patented form of sheet glass produced by Corning Incorporated. This is a specialized glass that is used in many technological applications such as phone and computer screens. Gorilla Glass has been used in 4.5 billion devices worldwide in over 40 major brands, and it is currently on its fourth generation of material. So what are the performance requirements? Requirements include high scratch resistance. Devices using these are often placed in pockets with other items such as keys, which could scratch the screen. So this is the hardness of the material. High toughness. This will prevent cracking of the screen when a device is dropped or something drops onto the screen. This is the toughness of the material. High flexibility. This will prevent fracture when under flexural loads such as sitting on a phone screen. So this is the flexural strength of the material. Thickness, the ability to be manufactured into very thin sheets, or the workability of the material. Cleanability, must be able to easily remove smudges on the surface, so the chemical stability of the material. And optically clear, this glass will act as a screen for a phone and therefore must be completely clear. And this is the optical properties of the material. So what is it made of? Gorilla Glass is a form of soda lime glass that has been strengthened to improve the properties of the material. Soda lime glass is prepared by melting the raw materials such as silicon dioxide or silica, sodium carbonate or soda, lime, dolomite, aluminum oxide or alumina, and small quantities of fining agents. Soda lime silica glass is the most prevalent type of glass that is produced. It is used for window panes, glass containers, and some glass bakeware. So how is it made? The production of the glass sheets is accomplished by the fusion process, which is a patented Corning Incorporated process. So how's this done? First, the ingredients are mixed together in the correct proportions into a vat. The vat is then increased in temperature until the materials have melted and homogenized. This is a very high temperature process, over 1,000 degrees Celsius. The molten material is then poured into a trough, or an isopipe, and allowed to overflow the sides. This overflow then runs down the sides and meets at the bottom, where it fuses together and draws down due to gravity. The thickness of the material can be tuned according to how fast the draw is allowed to happen. This process is completely hands-free and is completely operated by robots to cut the material. Other possible methods. Traditionally, sheet glass is produced by the glass float method. This starts with the batching of the materials, where the raw ingredients are mixed together in the right proportions and transferred to the melting process. The temperature of the ingredients is increased to 2,900 degrees Fahrenheit, where it ensures that all of it will melt uniformly. This molten glass is then poured onto a molten tin bath and spread out until the top and bottom layers of the glass are parallel with each other. To tune the thickness of the glass, top rollers on the glass surface stretch the glass until the achieved thickness is attained. This glass has to then be cooled in a long conveyor process so as to not introduce thermal shock on the system. Once the glass has reached the appropriate temperature, it is sectioned and packaged for delivery. Strengthening. After the glass is formed, it is toughened by ion exchange, increasing the strength 6 to 8 times, and this is explained here.
We do. Well, we identified that compression is easy for glass to handle, but tension is a problem because it pulls open those defects and causes a failure. So if we could somehow eliminate the tension force, then we could effectively make the material stronger. And there's a clever way to do this with a chemical process. Most common pieces of glass in the world have had sodium added to it to lower its melting temperature. So pure silicon dioxide is great, but it melts at such a high temperature it's difficult to work with. So we add sodium oxide in addition to lots of other things to lower the melting temperature. So here's a diagram of what that might look like. This is a slab of glass here, and the small circles inside are sodium atoms. And this chemical trick involves submerging the piece of glass in a potassium salt. So these larger circles are potassium atoms. And through the natural process of diffusion, some of the potassium atoms will take the place of the sodium atoms in the piece of glass. So what's happening here is these larger potassium atoms are being shoved into the spaces where there used to be just a very small sodium atom. And the effect is that we're basically shoved the glass, put the glass in compression by jamming these larger atoms inside of it. Now this process happens at a temperature lower than the glass softening point. So the glass is still hard when this is happening, and as we're shoving in these larger atoms, the glass is becoming increasingly put into compression. However, the center of the glass is not affected by this process as quickly, because this is like a diffusion process, and so it takes a while for these potassium atoms to work their way into the glass. So if we cancel the process after a certain amount of time, the center of the glass will not have this effect at all, and the edges will be in compression. So after the treatment, what we have is something like this, where the edges of the piece of glass are in compression, and the center of the glass is actually in tension because of all those extra atoms that we jammed in around the periphery. And this is true around the edges too, but I'm just showing it in one direction. So later, when we load the piece in bending, the top gets to be even higher in compression. The center is still in tension, but the bottom layer, which would normally be in tension in a bending situation like this, is now either neutral, or at least it's offset quite a bit. Because of that residual compression is sort of canceling out the tension that would be created by this loading scenario. So we've effectively strengthened the piece of glass by preloading it in compression. We're able to get rid of some of that tension loading. Another way to think about this is that the compression that we've added to this edge of the glass helps close the cracks. So when we put this in bending, this crack here, the defect, doesn't shoot up through the glass and cause breakage, because we're in compression here and it's actually sealing the cracks shut. The process is pretty straightforward. I set up a stainless steel container in a small kiln and added to it some potassium nitrate that I bought on eBay. I leaned the glass microscope slides against the stainless container and then turned the kiln on and set it to about 425 degrees centigrade. After the kiln came up to temperature, I opened it up and noticed that the potassium nitrate had quite a few impurities floating on the surface, so I fished those off and then added the slides to the now molten potassium nitrate. Since the process was going pretty well, I also upped the temperature to 450 degrees. After 3 hours at that temperature, I fished the slides out and let them cool as slowly as possible, but I didn't do anything special like put them into a temperature-controlled chamber. I just put them out in air. After they cooled down naturally, I washed the slides off in tap water and then loaded them into the test rig and tested their strength. So, did we just make Gorilla Glass? No, not quite. Actually, Gorilla Glass is a proprietary blend of ingredients. It's actually the starting point of the glass. The chemical strengthening that I've described in this video has long been out of patent protection, and lots of people do it. The special thing about Gorilla Glass is that it has a very unique set of ingredients that make it especially amenable to this chemical strengthening process.
Other products. Corning has just started using this type of fusion process in ion exchange to create windshields for high-performance vehicles. Chemically strengthened glass through ion exchange is also used in aircraft canopies for some jet aircraft. Book resources. So in the book there are several chapters that deal with glass and glass production, specifically Chapter 7, which provides details for ceramics, including glass, Chapter 12.2, which provides material on glass processing, including the glass float method, and then there's Chapter 27.2, which explains the ion diffusion mechanism and how it can be used for metals, but the concepts are transferable to glass. Select problems. There are several problems in the book correlated to this processing. So 12.7 in the book. There are several ways of shaping plate or sheet glass. Name and briefly describe them. So there's rolling of flat plate. Molten glass is rolled to form a continuous sheet. There's the glass float process. Molten glass is floated on a molten tin bath to form a continuous sheet. And then the fusion process, which is not in the book, but the one that Corning uses. Molten glass is allowed to overflow from a trough, fused at the bottom and allowed to stretch to its desired thickness. There's problem 12.1. What is the predominant chemical compound in almost all glass products? The answer is silica, or SiO2. And 7.15. Define glass. Glass is an inorganic, non-metallic compound that cools to a rigid condition without crystallizing. And here are my references. Thank you.